We all know the fundamental theorem of integral calculus, which connects the differentiation and integration. In essence, it says how the integration is an antiderivative. Now we will look at how far this fundamental theorem of integral calculus is true in the context of Lebesgue measure. So we will be proving a fundamental theorem in terms of Lebesgue measure. The hard work is already done through Lebesgue differentiation theorem in the first form. So you can quickly refer that. Let f be a Lebesgue measurable function. It's in L1 of R, and define a function using this function. Consider f integration with respect to the Lebesgue measure from minus infinity to x. Call this as a function of x. So define a new function g of x, integrating the function with respect to the Lebesgue measure from minus infinity to x. Then suppose B is a point in R at which f is continuous. Then two conclusions: g is differentiable at A, and the derivative at that point, g is differentiable at B, and g dash at B is f at B. The strategy of the proof is to start with the necessary calculation, necessary estimate to say g is differentiable at a point, and somewhere in between you need to use the fact any constant function is equal to its average value in a small interval, and use the assumption of continuity to get a better estimate. Let's start with the proof. Start with the estimate to say that g is differentiable at the point B, and if that derivative is equal to the function f of A, then I need to estimate this. So by definition, this is now notice, using the property of the Lebesgue integration, we can see it is same as b to b plus t of now we use the fact that f of b, I can write it as, remember f of b is just a constant function, so that is same as average value between any interval, and I need to divide by the length of the interval. So this is the first one, is integrating f with respect to the Lebesgue measure. Second is integrating the constant function f of b with respect to the Lebesgue measure. Now again use the property of integration to get now use the monotonicity. Now look at the interval where I am integrating b to b plus t, and hence we are already familiar with this information. I can take the supremum and push it out, so it is supremum of in the interval. And what we end up is that is nothing but the length of the integral. Just end up with supreme of f of x x is in this interval r, which is same as saying now we use the fact, since f is continuous at b, given any epsilon, there is a positive delta, such that whenever x minus b is less than delta, f of x minus f of b will be less than epsilon. If we choose t such that mod t is strictly less than delta, then the above estimate tells you is less than or equal to epsilon. Equivalently, when t is close to 0, this expression inside the blue circle goes to 0. That is what we want to prove. And hence the estimate goes to 0, since epsilon is arbitrary. This number limit exists, which proves both that t is differentiable at that point and the derivative at that point is also f of a. Starting with the same estimate, and if we reach up to this stage, we can also estimate it differently. Observe, this is in the form of Lebesgue Differentiation Theorem's first form. It says that this limit as t tending to 0 is 0. Hence, we get as t tending to 0 by first form. But only catch, or only point more to be careful, is that this estimate is almost everywhere, and hence we get the following theorem. F is in L1 of R, G as defined above, then G dash of B is f of B almost everywhere. This is usually referred as second form of Lebesgue differentiation theorem. Another immediate realization in the same lines of thinking is if I start estimating again use the fact that f of b is constant, so I can write it as average in this interval. Look at, I am dividing by the length of the interval 1 by 2t. Which is by the first form of Lebesgue differentiation theorem, this goes to 0. What this establishes is if f is in L1 of R, then the value of the function at any point is just the average as the limit t tends to 0 in almost everywhere sense. The set of rationals in real numbers is a measurable set which has its presence in every interval. One can ask questions: does there exist a measurable set such that the Lebesgue measure of this set intersecting with 0b is b by 2 for every b in 0 1. That means E has half of the elements of any closed interval 0b. Does there exist such a measurable set? For example, the irrationals, if you consider, all of them have full measure. Now we are asking slightly lower. Instead of full, can I have half? And the answer to this question is through Lebesgue Differentiation Theorem. Suppose such a set exists, then consider characteristic function of that set and define this function as usual. Lebesgue differentiation theorem concludes almost everywhere. Look at the right hand side. This function always takes either value 0 or 1. But what is the left hand side? So look at the left hand side and calculate what is g of b. It is minus infinity to b, characteristic function of e d lambda. Remember, E I am considering a subset of 0 1, so this is going to be E intersection with 0b, that measure by the definition, and I assume that this is b by 2. So g of b is b by 2, and hence g dash of b is 1 by 2. Now notice the left hand side is 1 by 2 and the right hand side is either 0 or 1. Even in the almost everywhere sense, they are not equal anywhere, and hence it shows you cannot find out such a measurable set. How about replacing 2 by some other number?